We'll talk now about special addresses. We have some IP addresses that are reserved for special purposes. We have this host address. This host address is the only address in the block 0000/32. This is called, this host address is used when you send a request and you don't know your IP address, so you use this as your IP address. This is called this host address. Okay. Limited broadcast address, the only address in the block 255.255.255 all ones /32. This is called limited broadcast address. It is used when a router or a host needs to send a datagram to all devices in the network. But the routers in the network, however, block the packet having this address as destination, and the packet cannot travel outside the network. So this packet will only travel inside the network. So it will go to all the hosts in your network, but will not go to the internet, because if it can go over the internet, then these requests or these broadcasts will flood the internet. Therefore, they will be stopped at the edge of the network. We have loopback address. The loopback address, this block which starts this IPC 127.0.0.0/8. So means this 8 is net ID. So this is net and this is host. So you can have 2 to power 24 IP addresses in this block. It's a big block. This is called loopback address. A packet with one of the addresses in this block, so you can have, as we said, 2 to power 24 addresses in this block. If you have the IP as in this block as your IP, it will never leave the host. So if you assign an IP of this IP to your network interface card or whatever, your request will not go to the internet, will not leave the host, will only remain inside. Any address in this block is used to test a piece of software in the machine. For example, we can write a client and server application, and before you put the server application on another device, you can assign the server application IP address in this block and your client an IP in this range, and you can test the software on your computer before deploying it on another device. I'll open just. If you use, for example, one second, open the command and ping localhost. So what you'll get? So I'll share the screen with you. So if you ping localhost, you'll get reply. Localhost is actually 127 normally is 001. See? Even if you don't have connection to the internet, this is called loopback address. You'll get a reply. Okay, this not does not mean you are connected to a network, or it's just for testing software and hardware. So if you have a device, you assign it this IP in this block, and then you can test if the software and hardware all work properly. This is called loopback address. We have private addresses. You have to remember these also. So we have several blocks, 3 blocks of private, or 4 blocks, sorry, of private addresses. One is this block, which means, you see, 8 bits for network, and then these are all for host. So you have 2 to the power 24, of course, here again. And you have this block, so 12 bits for network and the rest for host. And then this one, 12 for, 16 for network, 16 for host. And the last one, this one again, /16, 16 for network and 16 for. You see, this IP is famous. We use it as in our LANs and local area networks when we have NAT. This is used mostly in routers. For example, you see most routers will have IP address 0.1 or 1.1 or 10.1 or something like that. And if you check your connection, maybe now your IP, if you are using DHCP, you've been assigned an IP in this range. This is a private, called private IP addresses. If you cannot access the internet with these IPs, they are not routable. When they go to the internet, routers on the internet will discard them. So we need to use something else with these, which we'll explain later. We call it NAT, Network Address Translation. We have to translate this private address into a public address so that it can be routed. We have multicast addresses. The block 244.0.0.0/4 is reserved for multicast address. You need to remember these private addresses, and you have to know this block. So we talk now about DHCP, Dynamic Host Configuration Protocol. This is very important, and nowadays we always, when you connect to an internet, you're never bothered with assigning IP addresses or subnet mask. Why? Because you're using this protocol, DHCP. DHCP will automatically assign IP address to your device. This is very convenient. Actually, we rarely use manual IP addresses for clients. Only in, for example, in a managed network where you have servers and an administrator will assign IP addresses manually. Address assignment in an organization can be done automatically using this protocol. DHCP is an application layer protocol, okay? So this is application layer, but it provides service to the network layer using the client-server paradigm that actually has TCP/IP at the network layer. So it's application layer protocol providing service to the network layer. DHCP can be configured to assign permanent IP addresses to the hosts and routers. DHCP can also be configured to provide temporary on-demand IP addresses to hosts. This allows an ISP with, for example, 1,000 granted addresses to provide services to 4,000 households, because not all of the 4,000s are connected to the internet at the same time, assuming 1/4 of customers have the internet, use the internet at the same time. DHCP can be used to provide the computer address, the prefix, which means the subnet mask, the address of the router, the IP address of the name server. All this can be obtained through DHCP, not only the IP address. So when you get a DHCP address, you can get more information about it. So you can use name servers or the router or the gateway. The message format of DHCP, this is the message format or the header of the DHCP protocol. We have the first byte is opcode, operation code. Is you either request or you have a reply. H type, hardware type, is it Ethernet or token ring or whatever. H length is the length of the hardware address. H count is maximum number of hops. Sometimes you don't want your DHCP server to provide address to devices outside your network. Therefore, you can limit the hop count. So when it travels across 3 routers, then it will stop. The transaction ID is an integer set by the client and repeated by the server. So when you request an IP address, you set a transaction ID or integer number, so that when the server replies, it will use the same same transaction ID. Time elapsed is the number of seconds since the client started to boot. When you start your computer needs an IP address, so it will send a request, and in that request it will tell how many seconds this computer started to so that the server will know if this request has been waiting for a long time. Flags, there are different flags. First bit defines unicast or multicast. Other 15 bits not used. So it's only the first bit. You see 16 bits. First bit is used to tell if this request, for example, is unicast or multicast. We'll see in the next slide when we need unicast and when we need multicast. Client IP address. If you don't know your IP address, you'll use what? 0, which is this IP address. Because you don't know your IP, you use 0. Okay? First time when you send a request. Your IP address, the client IP address sent by the server. So when the server replies, it will tell the client that sent this request, this is your IP address that you can use. Server IP address is the IP address of the server that provided the IP, this IP. Gateway IP address is the address of the default router, if you have a router going to the internet, for example. Server name, domain name of the server, and then these other fields. We are interested in these mostly now You have to know how this works. So the operation of DHCP. I want you to catch some DHCP packets when you connect to the network using Wireshark, of course, and then filter them just to collect the DHCP packets and see how this process is done. So first, when you boot your computer or your computer is connected to a network or a Wi-Fi router, it will send a DHCP discover packet. In that, you will have a transaction ID, as we said. Lease time, there is no lease time because the server will do this. Client address, your address, server address, and then you have, you see, source port. This is application layer protocol. So we go through transport up to application. So you need ports also. So the source port that this request will go out is 68. The destination port in the server which listens to this request is 67. Source address, you see, you don't have address, so you use what? A 0, which is, if you don't know your address, you use that address. Destination address, you don't know the address of the server yet. You're just searching or sending DHCP discover. So you'll use broadcast. This broadcast will arrive at all the devices on your network. Okay, so this is limited broadcast address. All the devices on your network will receive this broadcast. Okay, because you don't know which the IP address of the server, therefore you send a broadcast. Now, if there is a DHCP server on the network, it will listen on port 67 and see there is a DHCP discover. So it will reply. If it has got an offer, it will reply with an offer. The offer will see the IDs are the same. It will tell the lease time. This IP which I am offering now is valid for this time, amount of time. Your address is IP address that you can use. This computer can use this IP. I'm offering this address. And server, this is the server that offered this IP address. Now you see the source port, here it was 67 because you see destination, but the destination port, it should go to this port. The request came out from this port. So when you receive the request, it should go through that port. Now source address again is this one, but destination is broadcast. Why? Because there may be other DHCP servers on the network. In this case, you are telling them that I'm offering this client an IP address and this is my offer. If another server on the network has got better offer, it can also reply to this DHCP discover and give their offer. Now, when the client receives the request, the offer, it will reply with a DHCP request. You see here, transaction ID is the same. Lease time now is that lease time. Client address, you see, this is the client. It offered this IP, so it used the IP to communicate now. It does not use the 0 anymore. The client is now assigned this IP. Your address, and then server address, who sent this, this server here, server address. Now again, the source port and destination ports are the same as before. Source address, as we said, the client now. And the destination is broadcast again. Why? This computer now knows which computer this IP send it the address. It's not going to use that as destination, but it will use broadcast so that it can tell the other servers that it used this IP address now. Okay. Now, after the server receives this request, it will send DHCP acknowledgement, or maybe it will send a DHCP negative acknowledgement in case it can no longer provide this offer. So if it can't provide the offer, it can guarantee that offer, it will send a DHCP acknowledgement. The DHCP acknowledgement now contains same as transaction ID, lease time. Your address is the same as before, same. And the server address, this is the same server. Now source address, it knows, this is the source. And destination is broadcast again, so that all the servers, DHCP servers, know that this server offered a valid address to that client. Of course, if the other servers on the network see this DHCP acknowledgement, they will no longer send DHCP offers to this client, because they know this client now is assigned an IP. This is how DHCP works. This is the exact explanation as we did. This is some packets that I captured using Wireshark. I want you to do it on your computer when you connect to the internet and collect the packets, and then analyze these packets. What is, you see, DHCP discover, offer, request, acknowledgement. Capture all these packets and see what they contain. Okay, analyze them. This is a homework for you, so you have to do it on your computer. Capture the packets and see what they contain. All these packets, analyze what's going on, and you need to submit it. Okay, so everyone will do on their own computer. When they connect to the network, you for sure have these packets and you can capture them. This is so the last thing we'll talk about network address translation, or NAT. NAT is very important. We always use NAT in our networks, in local area networks. So let's assume that an ISP, Internet Service Provider, has granted a small range of addresses to a small business or household. If the business grows or the household needs a larger range, the ISP may not be able to grant the demand because the addresses before and after the range may have already been allocated to other networks. You see, when we said classless addresses, when you are granted a block, this block should be contiguous. So maybe another organization requested the next block. So if you request more addresses, you may not have this next block because this has been given to another organization. Therefore, it's important to use NATs. In most situations, only a portion of computers in a small network needs access to the internet simultaneously. For example, you are looking at home now and you're connecting to the internet, but at the same time only several of your computers at home or devices connect to the internet. Sometimes they may sit idle. They don't do requests to the internet. Therefore, you can use the limited number of public IPs and share them among many devices. The number of allocated addresses does not have to match the number of computers in the network. For example, if a small business with 20 computers, the maximum number of computers that access the internet simultaneously is 4, this business can use TCP/IP protocol for both internal and universal communication. The business can use 20 or 25 IP private addresses for internal and use these 4 public IP addresses to communicate to the internet. Network address translation, or NAT, can provide the mapping between the private and the public. So these private cannot access the internet. They will be dropped. So you have to, these public IPs will convert this private into public IP that is routable and can go over the internet. This process is called NAT. The private network is invisible to the rest of the internet. The rest of the internet sees only the NAT router with the address. For example, in this case, this is the router. You see, these devices, these IP addresses cannot go to the internet. If they connect directly, their packets will all be dropped because they're using, you see, this is private IP address. Remember, you see, this is a private IP address, 172.16. So these are private IP addresses, and you cannot use them on the internet. So to communicate with the internet, you need to use NAT. Or a network address translation. So in this case, for example, this device source is this, wants to communicate to the internet. So the source IP address is this. Okay, when it goes to the router will not use this as source. It will use this public IP as source address. Because this, if you use this, it will not be routed. It will send the request on behalf of this device to the network, to the internet. Then when you get the reply, the destination will be this, okay, not this. The router using NAT will move this packet to this device because it has got a translation table that it will use to forward the packet, as we'll see now. A translation, there are different ways to use the translation table using one IP address. So if you have one public IP, okay, in this case you have 2 columns, the private address and the external address, or the public. So let's say here, first, this is the private network, source address, which is a private, and the destination is a public on the internet. So somewhere here, the IP is, you're connecting with Google, for example, on the internet. So this is your IP, this is the Google IP address. Now this will go, you see, to the router. The router will check. You see, this is the IP is private. It will use the public IP now, and the destination is the outside network, and send it over the network. Now, when you receive, when this replies with the destination will be this one, not that one. Okay, when you receive a reply, the router will have now this translation table. This IP requested this IP, so this is stored in the router. When the request arrives, this is the reply. The source was this, which is the destination that you wanted, and the destination is the router. So the router will check in its table who requested this IP. In its who requested this IP, it will see that this private network or client requested this IP. So it will forward the answer to that device, to that private network, and the communication will be okay. In this scenario, the problem is at any time only one device can connect to the internet, because you only have one IP, public IP. So if two devices want to communicate to the internet at the same time, you have one IP, you have to offer it to one of them, and the other one will wait until there is time. This is the disadvantage. The other way is to use pool of IP addresses. In this case, the router can use 4 or whatever number of IP addresses public, and it will have and it can do several requests to the internet at the same time. To remove this restriction, NAT routers can use a pool of global addresses. For example, instead of using only one global address, this is the one that we used in the other example, the NAT router can use 4 addresses, all these addresses. In this case, 4 private networks can communicate with the same external host at the same time, because each pair of addresses define a separate connection. No more than 4 connections can be made at this, to the same destination. Okay? So in this case, in the previous one, because you see, this private requested this public. If another private address, 172.18.3.2, wanted to access the same network, when the reply arrives, you don't know to which one you will forward the reply, because the same destination send you the reply, but you have 2 private addresses that requested the same destination. So to which one you forward, you don't know, to forward it to this one or to this one. To remove this ambiguity, we can use a pool of public IP addresses. So if 2 devices wanted the same destination, one can go through this public IP, and another one can go through another public IP. So here you will not have ambiguity in this translation table, because they'll have different fields, different addresses here. Okay, I will see the table. I think in the next one it will be clear. No private network host can access 2 external server programs. The disadvantage here still is that No two private network host can access two external server programs like, for example, HTTP or Telnet at the same time. Two private network hosts cannot access the same external server program at the same time. This is with the pool of IP addresses. The other way is to use IP and port addresses. This is the most widely used way. NAT. This is more flexible, and you don't have ambiguity. To allow many-to-many relationship between private and host, external